Hello and welcome to this chemistry lecture series. Today we're going to go over chapter 8.3, which is going to start to cover the mathematics that go along with equilibrium. We're going to look at the equilibrium expression, which is the main equation we use for equilibrium, as well as what we call the equilibrium constant, which is one side of that equation. So let's get started. So equilibrium expressions and equilibrium ratios are all about the ratios of the concentrations of the reactants and products at equilibrium. Their concentrations at equilibrium might be different depending on how much the initial concentrations were. So for example, if we had hydrogen reacting with iodine to make a hydrogen iodide, depending on the concentrations of hydrogen, iodine, and hydrogen iodide initially, the concentrations of these compounds are going to be different at equilibrium. So for example, here on this chart, we have four different examples of different amounts of hydrogen, iodine, and HI at equilibrium. These are all at equilibrium. Don't get me wrong, equilibrium can be reached with a number of different concentrations for the exact same equation. It will depend on how much originally did we have of the reactants and the products. So did we start with nothing but reactants and we had zero of the products? Did we start with nothing but HI and we had none of the reactants initially? Or did we start with some combination of hydrogen, iodine, and HI in the reaction vessel? Depending on those concentrations that we had initially, once the equation reaches equilibrium, once the reaction has reach a dynamic equilibrium we spoke about earlier, we will get different amounts of each of the reactants and products. However, the ratios of the concentrations at equilibrium, when arranged in a specific way, are always going to be the same regardless of where we started and what concentrations we had at equilibrium. So for example, here, if we do the product square, so the concentration of HI at equilibrium squared, and we divide that by the concentrations of hydrogen and iodine, regardless of which equilibrium we're using, we always get roughly the same number. So if we do 8.64 times 10 to the negative 3 squared, divided by 0.68 times 10 to the negative 3 times 0.68 to the negative 3, we get 161. That's the ratio. If we do the next equilibrium, 6.30 times 10 to the negative 3 squared, and then we divide that by 0.5 times 10 to the negative 3 times 0.5 times 10 to the negative 3, we get 159. Very similar ratio, very similar amount. And if we do that for the other two equilibriums, again, we get 161, 160, very similar amounts. We get very similar ratios. And that's because this ratio, this way of putting the concentrations together, tells us a lot about the equilibrium. That ratio that we used in the prior example is what we call the equilibrium expression. The equilibrium expression is essentially a ratio of the products concentrations in a reaction divided by the reactants to their coefficients as an exponent. So if we have, for example, Ma plus Nb, where A, B, C, and D are reactants and products. A and B are reactants, C and D are products. M, N, P, and Q are their coefficients, so the 1, the 2, whatever number might be in front of them when we balance the equation. If we do a ratio, and a ratio is just really dividing two things, right? So if we do a ratio of the product concentration, so the concentration of C times the concentration of D, to their coefficients as an exponent, so C to the P, because P is the coefficient for C, D to the Q, because Q is the coefficient for D. And then we divide that by the reactants in the same manner. So we have the concentration of A to M as an exponent, the concentration of B to N as an exponent. That's what we call the equilibrium expression. It's a simple relationship that links Kc to the equilibrium concentrations of reactants and products and their stoichiometric equation. This is the official definition. Now, what is Kc? Kc is what we call the equilibrium constant. So Kc is going to be the equilibrium constant. So anytime you see K in this chapter, it's going to mean equilibrium constant. And it's a constant which is calculated from the equilibrium expression for a reaction in terms of concentration. So essentially, Kc is the constant that we get when we divide the concentration of the products to their coefficients as an exponent, divided by the concentration of the reactants to their coefficients as an exponent. Remember, these brackets mean concentration. So A in brackets means concentration of A. B in brackets means concentration of B. So we're working with moles per cubic decimeter here. This is how we can look at equilibrium mathematically. Whenever we do a ratio of the products over the reactants concentrations to their coefficients and exponent, we always get, regardless of what the equilibrium concentrations are, we always get the same ratio in this way, which is what Kc is, equilibrium constant. So if we go back real quick and we look at what we were, the data we were looking at before, these are the concentrations of 4 different equilibriums that were reached by mixing different amounts of hydrogen, iodine, and HI. Well, if we do the equilibrium expression for this, which is what this ratio right here is, HI squared, because the coefficient for HI is 2, divided by H2 and I2 concentrations, because these don't have coefficients, are 1, that should always give us the same ratio regardless of what equilibrium we use and how we got there. That ratio would be the equilibrium constant. So this 161, 115, 159, 161, 160, these are the equilibrium constants for this reaction. Obviously, they're not going to be perfect. They do vary a little depending on which, like mathematical and both practical and mathematical error, but they are going to be roughly constant. They will roughly always going to be the same. So we look here. We can see an example of another equation. So if we have 2 sulfur dioxide plus oxygen yields 2SO3, and we can tell this is an equilibrium equation or reaction because of the double arrows. The question here is to write the expression for the equilibrium constant Kc, so that has to write the equilibrium expression for the reaction between SO2 gas and O2 gas to produce SO3 gas. So they're essentially asking us to write the equilibrium expression for this reaction right here. Now this should be fairly straightforward because remember, all we have to do this is do the concentration of the products to some exponent x, depending on what the coefficients are, divided by the concentrations of the reactants to their exponents, y. So what does that mean? That means that the equilibrium expression here is going to be, let's raise this real quick, is going to be Kc is equal to, because Kc is the equilibrium constant, the product concentration, the product here will be SO3, so it will be the concentration of SO3, and because the coefficient for SO3 is 2, we put this to the second power. Let's make this a little more even here. Divided by the reactants to the same thing, to their coefficients of their exponent. So the reactants here are SO2, so we're going to have concentration of SO2, and the coefficient for SO2 is 2, so SO2 squared, times the concentration of O2, which is the other reactant. And this was to the first power because there is no coefficient in front of the O2. So here we have that Kc is equal to SO3 squared divided by SO2 squared times O2. And that's our equilibrium expression for the equation we were given here. And then we always got to remember, in this case, they gave us the Kc is equal to. We always got to remember to put it if they don't give it to us, because that Kc, the equilibrium constant, is equal to this ratio, is part of the equilibrium expression. So we can see here that Well, we got, don't forget the brackets, because brackets mean concentration. So when we put SO3 in brackets, it means concentration of SO3. If we don't put the brackets, then we are not doing this correctly, because if we just put SO3, it could be volume of SO3, it could be concentration of SO3, it could be mass of SO3, it could be any one of those things. So make sure you remember your brackets. Make sure you remember that the exponents are the coefficients for that particular reactant or product. And remember, we always do products over reactants, and that's going to be equal to Kc. Let's keep going here. So equilibrium concentrations, and this is where you need to start to make sure that you are aware of what you're solving for. The equilibrium expression requires us to use the concentrations at equilibrium. Like we discussed in a prior video, the concentrations could be of equilibrium or it could be initial concentrations. When we looked at those graphs, the concentrations changed until equilibrium was reached. We start with a specific amount of reactants and products, and then they're going to undergo a change until they reach equilibrium. So oftentimes with these type of questions on this exam, we will be given initial concentrations along with equilibrium concentrations. We'll be given a mixture of them. And in order to figure out what type of or what the equilibrium concentrations are once the equilibrium has been reached, we need to do what is called an AICE table. Now, an AICE table might sound scary, but it's actually a very simple table that helps us keep track of concentrations. AICE stands for initial, change, and equilibrium. The initial row is going to essentially be us putting down how much concentration of each reactant and product we had initially. The questions will usually tell you you have a specific amount initially of a reactant or product, and so you will put those concentrations in this row, and that we represent them here with AICE for initial. If the reaction or the question does not mention initial concentrations, then we assume that they're going to be 0 for that reactant or product. Because if they're not mentioned, then it's because there is none. The change row is going to talk about how much do these change by. This is almost an equation. Because for some of these reactants and products, we will be given equilibrium amounts, which are the last row. So we'll be able to put those there. Well, what you have to realize is that when we have an equilibrium, from the initial amount to the equilibrium amount, from the initial concentration to the equilibrium concentration of any reactant or product, a change will be made. So, for example, if we initially had, let's say, 1 molar D, and then at the end, once equilibrium was reached, we have 0.5 molar D, then the change here would have been of negative 0.5 molar. We lost 0.5 molar. That's what the change row is talking about. It's talking about figuring out what the changes with a reactant or product that we have both the initial and equilibrium concentrations for. Because the changes and the change row with equilibrium with an AICE table, it's always going to be a ratio for all different reactants and products. What are those ratios? Those ratios are their coefficients. So let's say Q and P are the same. If Q and P are the same, then the change for D and the change for C will be the same. And so if D changes by negative 0.5, so will C. But that's only if, let's say, P was 1 and Q was 1. If M was 2, then the change for A will be twice as much as it was for D, so it will be 1.0 molar, but it wouldn't just be the same, it would actually have the opposite sign. It will be positive 1.0 molar. Why? Not only is M twice as much as Q, so the coefficient of A is twice as much as that of D, but A is a reactant and Q is a product. So they will have different signs because if we're losing concentration of a product, that means the reverse reaction is happening, and so we're gaining concentration of the reactant. Now, this can be very hard to visualize with theory like this, theoretical scenarios. So let's look at an actual question that is going to use an AICE table. Because like I said, AICE tables can be very scary, but once you understand how they work, they're actually very useful tools, and they're very easy to fill out because they're visualization tools. They help us keep a tally of the concentration of the reactants and the products, and their concentrations initially, their concentration at equilibrium, and therefore how much do they change by. So let's look at our question. So this is the type of questions you will see. Now, this question is very lengthy, but one of the things that you got to realize as well is that when we work with equilibrium and when we work with AICE tables, a lot of the time we can work with them not just with concentrations, but also with moles. If there's all in the same container, we can also work with them with pressure if we're working with gases. So AICE tables are very versatile, and we can use them in a lot of different ways. But let's start with the most basic way. So let's read this question thoroughly first, and we'll highlight some things here. So 2 moles of SO2, so that's useful to know. We have an amount here. 2 moles of SO2 and 2 moles of O2, so again, useful to know, are sealed in a container with a suitable catalyst at a constant pressure and temperature. Again, that's things that we are good to know, but they're not really going to be useful here. So we have moles of SO2 and moles of O2, which are the reactants in this case. So we should probably highlight them in yellow as well. So we have moles of O2 and moles of SO2, which are reactants. And then if we keep reading, it says the resulting equilibrium mixture contains 1.98 moles of SO3. SO3 is our product here. So we'll highlight it in blue as well. So it tells us we have 1.98 moles of SO3. If you noticed at the very beginning of those sentences, we have some key words here because it says the resulting equilibrium mixture contains 1.98 moles of SO3, meaning these 1.98 moles are at equilibrium. On the other hand, this first part says 2 moles of SO2 and 2 moles of O2 are sealed in a container. That means it's not after equilibrium has happened. These 2 moles of SO2 and O2 are before equilibrium has happened, meaning that these are initial values. These are initial values of SO2 and O2. We know that because this sentence, the resulting equilibrium mixture, tells us that 1.98 is after equilibrium has been reached, whereas the 2 moles and the 2 moles just say are sealed in a container. So we can assume that they're sealed in a container initially before equilibrium has happened. So if we set up an AICE table here, the very first thing that we need to set up is the SO2, O2, and SO3 in the top row, because those are our reactants and products, and then our ICE rows, initial, change, and equilibrium. If we keep reading through this question, the total volume of the equilibrium mixture is 40 cubic decimeters. So we could divide each one of these by points or by 40 to get a concentration. And that might be something that we want to do later. But if we keep reading the actual question, calculate the amount in moles. So this is where the key vocabulary comes in. Calculate the amount in moles. Meaning we don't want equilibrium concentrations, we want equilibrium moles. So we could convert everything to concentration by using these 40 cubic decimeters. But at the end of the day, we're going to have to reconvert that back to moles by multiplying by that 40 cubic decimeters. So it's really pointless to do that. We can use an AICE table with moles as long as everything is in the same mixture. And because equilibrium mixtures are always going to be all in the same mixture, we can always use it with moles or with concentration. What's important is that if we're going to use them with the equilibrium expression we talked about earlier, the equilibrium expression specifically needs concentration, but the ICE table doesn't. We can do an ICE table with moles. So let's start putting things where they belong, right? We know that the 2 moles of SO2 and the 2 moles of O2 are initial concentrations. So we can put the 2.00 moles of SO2 in our ICE table as an initial concentration. We can put the 2.00 moles of O2 as an initial moles for oxygen. And then we have the 1.98 moles of SO3. We're not told what the initial concentration of SO3 is. We're just told that the equilibrium mixture contains 1.98 moles of SO3, which means that we can assume that the equilibrium moles of SO3, the initial moles of SO3 are 0. Why? Because it's not mentioned. They don't tell us that there's any SO3 in the initial mixture. And so we can assume that there is none. And so we put 0 moles. We also know that the equilibrium mixture contains 1.98 moles of SO3. So that's something we can put in our equilibrium row. We have 1.98 moles of SO3. So we have now grabbed all of the information from our problem that is pertinent and have added it to our ICE table. This is where we can start to figure out what all of these empty spots are. Because the ultimate question here is calculate the amount in moles of SO2 and O2. So what we're trying to calculate here, what our ultimate goal is going to be, is to figure out what is the equilibrium moles of SO2 and what is the equilibrium moles of O2. That's what the question is asking us. It's obviously not going to ask us for SO3 because they're giving it to us, right? So we want to know what this box is. We want to know what this box is. So let's start looking at how we figure that out. So we need to use the information given to fill in the blanks. And the only one that we can fill right now is this middle box, because this is the change, right? We know that from 0 moles of SO3 initially, we ended with 1.98 moles of SO3 at equilibrium, meaning that the SO3 changed by 1.98 positive. We can equate that, or we can essentially relate that to an equation. Why? If we look at our reaction equation, we have the 2 moles of SO2 react with 1 mole of O2 to create 2 moles of SO3. Meaning that there is a 2 to 1 to 2 ratio between SO2 to O2 to SO3. That 2 to 1 to 2 ratio is going to reflect in the changes. Because why do these changes happen? These changes happen because equilibrium is reached. Equilibrium is reached by either the forward or reverse reaction happening. Meaning that if in this equation, this equilibrium, we made 1.98 moles of SO3, then that 1.98 moles of SO3 was made by the forward reaction that used up the SO2 and the O2. So the SO2 and the O2 are going to decrease in number of moles, and they're going to do so according to a coefficient in the equation. So if we go back, we can essentially set this positive 1.98 to be equal to positive 2x. Where does it positive 2x come from? The x just comes from a variable. We need a variable. We can call it x, we can call it y, we can call it whatever we want. So we'll just use x because that's what we use in math. The 2 comes from the fact that the coefficient for SO3 in the equation is 2. So that's why it's 2x, because the change is going to be twice the amount of something that had a 1 coefficient. And why is it positive? Well, it's positive because the change was positive. We're going from 0 to 1.98. We're adding number of moles. So that is going to be positive. So we can then look at the reactants. The reactants, SO2 initially, is going to have a change of negative 2x. Why negative 2x? Again, x is just the change variable that we're going to put as x because that's what we chose. Why 2? Well, SO2, like SO3, has a coefficient of 2. And so we are going to have that change be equal to the change for SO3. SO3 had 2x because the coefficient is 2. SO2 has 2x because the coefficient is 2. And so their changes are going to be the same, but the change for SO2 is not going to be positive 2x, it's going to be negative 2x. Why? Because since SO3, which is a product, change in the positive manner, we created the product, we created SO3. In order to create SO3, we need to use up the reactants because of 4 of the reactions happening. So the concentrations or the number of moles of SO2 and O2 are going to decrease. So this is going to be a negative 2x. Well, if positive 2x is positive 1.98, the negative 2x is going to be negative 1.98. So the change for the SO2 number of moles is going to be negative 1.98. And then finally for O2, it's going to be a change of negative x or 1x. Again, x is just a variable we chose. Why no number in front of the x? Because our coefficient for O2 is 1, meaning that the change for oxygen is going to be half that of SO2 or SO3 because the coefficient is half that of SO2 and SO3. It is a 2-to-1 ratio between them. And why negative? Again, because O2 is a reactant. Since the concentration of the product went up, then the concentration of a reactant like O2 has to go down. Since the change for O2 is negative x, then if 2x is 1.98, or if negative 2x is negative 1.98, then x, negative x, which is half of negative 2x, is only negative 1.98 divided by 2, or 0.99. Once we figure out these changes, once we figure out what x is, and then we put all the changes in there, the negative 0.99, the negative 1.98, we can then figure out what these equilibrium concentrations are going to be. Because if we started with 2 moles of SO2, and it changed by negative 1.98, 2 minus negative 1.98 is going to be 0.02 moles of SO2 that we have left over at equilibrium. If we started with 2 moles of O2, and then it changed by 0.99 negative, so if we subtract 0.99 from 2, we get an equilibrium concentration of 1.01 for O2. Or an equilibrium, sorry, number of moles, because we're not doing concentration right now. And so what is the answer to this? What is the number of moles of SO2? 0.02. What is the number of moles of O2 at equilibrium? 1.01. And so we can see here, those are our answers. So we're using the AICE table. We're going to use the one that we have both of the initial equilibrium reaction concentrations or moles for, to figure out what the change is going to be. So 0 to 1.98 is positive 1.98. And we're going to relate that to a mathematical equation, an algebraic equation of 2x because of the coefficient being positive, or because of the coefficient being 2 and the change being positive. And so from there, then we can say, okay, SO2 is going to be negative 2x because coefficient is 2 and it's the reactant, not the product, so it has to be negative. And so if 2x is 1.98, negative 2x is negative 1.98. And then for O2, because it's a reactant, it has to be negative. And because coefficient is 1, then it has to be negative 1x. So if negative 2x is equal to negative 1.98, then x is equal to 0.99, because we just divide by 2. And so negative 2x, negative 0.99. And then from there, we can figure out the equilibrium moles or the equilibrium concentration, depending on what we're using, based on the initial and the change. And that's how we use an AICE table in order to solve for equilibrium concentrations or equilibrium moles for a specific reaction and set of initial data and equilibrium data. All right, so that's one way we can use the AICE tables. Let's keep going. So let's look at the units for KCs, because the other part of the equilibrium expression that we haven't talked too much about is the equilibrium constant Kc. Kc can be used or can be found by using the concentrations of the reactants and the products at equilibrium, which we just looked at, we can find by using an AICE table. Well, once we have the equilibrium concentrations of the reactants and the products, we can plug them into equilibrium expression to find and calculate Kc. But because the equilibrium expression is going to be different for different reactions based on the stoichiometry of them, based on how they were balanced and the numbers of the coefficients, Kc can have what we call variable units. There are always going to be some combination of moles and cubic decimeters, but they are going to change and be essentially two different exponents. It does happen as well that Kc sometimes does not have units at all. So Kc could be calculated to have no units or to have some variation of moles per cubic decimeter to some exponent. So let's look at this, for example. This is the equation we were working with earlier where hydrogen and iodine react to make hydrogen iodide. The equilibrium expression we saw for this reaction was Hi squared divided by H2 over I2. Well, if we plug in concentration units in this equation, so any concentration is always going to be moles per cubic decimeter for Cambridge. So those will be moles per cubic decimeter squared divided by moles per cubic decimeter times moles per cubic decimeter. We would, once we simplify this, end up with moles per cubic decimeter squared divided by moles per cubic decimeter squared. Well, those two units actually cancel out when we divide them by each other. And so the Kc, the equilibrium expression for this particular reaction, has no units. Now, for this particular reaction, it doesn't, but for different reactions, it will. So let's do a problem where we not only find the value of Kc based on the AICE table we just did, but we actually look at the units. So let's look at this question. This is a follow-up to the question where we did our AICE table. So I have our AICE table from the prior question here. And I also have the equilibrium expression that we worked out for the first part of this problem here. So this is from the part 1 of this problem. You can see this is part 3. This is from part 2. So as is very usual in Cambridge, especially with equilibrium questions, these questions are going to build up on each other. So let's look at what our question is. Use your answers to di and dii, which are these two, to calculate the values of Kc for this equilibrium mixture. Give the units of Kc. So we need to figure out not just the value, the numerical value for Kc, but the units. So here we have the equilibrium expression that we worked on in part 1. And we have the equilibrium amount of each of the reactants and products. But you have to be careful. If we look closely at what we have here, for the equilibrium expression, we have brackets, which means we need to use concentrations. Whereas for the part 2 problem, we have moles as our answer for the equilibrium. So we need to convert all of these moles here into concentrations. If you remember from that first problem we did, that first problem told us that the volume of the mixture was 40 cubic decimeters. So that means that in order to convert all of these into concentrations, we need to divide every one of these numbers by 40 cubic decimeters. So when I divide the 0.02 by 40, divide the 1.01 by 40, divide the 1.98 by 40. Why by 40? Again, we're trying to get concentrations. So we're doing moles per cubic decimeter. So we divide by cubic decimeters. And why 40? Because this is the volume of the mixture. It's the overall volume of everything mixed together. And that volume means that every one of the solutions in the mixture has the same volume of 40 cubic decimeters. So we do 0.02 divided by 40. We are going to get, and I'm going to do this in a different color, that we have the concentration of SO2 is going to be 5 times 10 to the negative 4 moles per dm cubed. 1.01 divided by 40 is going to be 0.0253 moles per cubic decimeter. And then the 1.98 divided by 40 is going to give us 0.0495 moles per cubic decimeter. Once we have these concentrations, now we can use them, because these are still at equilibrium. Now we can use them in our equation. Because again, these are concentrations at equilibrium, all of them, not initial concentrations. So we don't use the first row, we use the third row. But they do have to be concentrations. So here Kc is going to be equal to the concentration of SO3 at equilibrium, which we said was 0.0495. So we're going to have here 0.0495 squared. And I'm not going to do the units in here because I'm going to do the units separately since we need to figure out what those are. And that's going to be divided by the concentration of SO2 at equilibrium, which is 5 times 10 to the negative 4. So 5 times 10 to the negative 4 squared as well, times the concentration of O2, which is 0.0253. So 0.0253, and this is not squared because O2 had a coefficient of 1. So Kc is going to be 0.0495 squared divided by 5 times 10 to the negative 4 squared times 0.0253. And we are going to get, as an answer here, 3.87 times 10 to the 5th. Oops, that's a 9. To the 5th. And that's our value for Kc. Now, this is our value for Kc. We also need to figure out what our units for Kc are going to be. So in order to do that, what I'm going to need to do, I want to do this in a different color. So let's do here, orange. What we're going to need to do here is we're going to need to essentially do the exact same math we just did, but instead of doing it with the math, we do it with the concentration units. So instead of doing 0.0495, the units for 0.0495 were moles dm to the negative 3 squared over, again, any concentration will be moles dm to the negative 3 squared times moles dm to the negative 3. So again, all we're doing is we're just substituting the numbers for the concentrations with the units of concentration. If we simplify this, we get moles dm to the negative 3 squared at the top. And then when we multiply something squared times 1, something to the first, we just get moles dm to the negative 3 to the third power. So what's going to happen here is that the second part, because notice what's in this parentheses is exactly the same. So you can imagine it being x. We have x squared over x to the third. That's going to simplify, that's going to cancel, and this is going to simplify to 1. So what we get is 1 over moles dm to the negative 3. Well, 1 over moles dm to the negative 3 is the same as saying moles to the negative 1 dm to the third. So our answer here, our units, is moles to the negative 1 dm to the third. because the 1 over moles dm to negative 3 flips those numbers. It flips the exponent signs, and we get this. Essentially, what we have here, to put it in a different way, is that we have 1 over mole per cubic decimeter. And if we divide 1 divided by a fraction, all we're doing is flipping the fraction. So we get dm to the third over moles, or mole to negative 1 dm to the third. And that's going to be our answer for the units. So if we look at our mark scheme now, we see that we get 3 points for this question, 3 marks. The first one is for correctly setting up our numbers, our expression with our concentrations instead of our moles. So notice they use the 1.98, 0.02, and 1.01, the moles, but they divide all of them by 40. Why? Because we just did that in a separate step here to get the concentrations and then plug them in. In the mark scheme, they're doing it all at once. So we get 1 point for that setup. We get 1 point for the answer, which we got 3.87 times 10 to the fifth. They have 3.88, and again, that's just a difference of how we did the math. It's just rounding error. That will still get the point for that. And then finally, we get our answer, which is dm to the third mole to negative 1. Or mole to negative 1 dm to the third. It doesn't really matter which order you put them in. But yeah, that's how we solve for Kc. That's how we find the equilibrium constant and its units for a problem like this. Notice this is a third part of a problem, and a lot of these equilibrium problems are going to be multiple parts that you end up building on each other. Now let's discuss what happens to the equilibrium constant whenever there's a change in concentrations. We discussed earlier in section 2 that whenever we cause a change to an equilibrium, Le Chatelier's principle says that that equilibrium will shift to counteract that change. But mathematically, why does that happen? The equilibrium constant, just like the name implies, is a constant. It does not change just because the concentrations of the reactants and the products change. So what exactly makes the equilibrium constant, or the equilibrium, shift if the equilibrium constant doesn't change? The change in concentration is going to happen in order to actually keep the equilibrium constant the same. Whenever we cause a change in concentration, so let's say we add iodine to an equilibrium of this reaction, we are increasing the concentration of one of the reactants or products. So if we had this equilibrium and we add iodine to it once it has reached equilibrium, Le Chatelier's principle said that the equilibrium is going to shift to use up that iodine that we added. The reason why is that by increasing the equilibrium concentration of iodine, the equilibrium concentrations no longer match the equilibrium constant. So what happens? The equilibrium shifts to use up that iodine, and also because it shifts by undergoing the forward reaction, also decreases the concentration of the hydrogen, while also increasing the concentration of the hydrogen iodide. This happens because we are essentially, by increasing the concentration of iodine, we are unbalancing this equilibrium, so it's no longer equal to Kc. Because Kc can change, what that means is that nature is going to shift this equilibrium to the right, the forward reaction is going to happen, to decrease the concentration of the hydrogen and the iodine and increase the concentration of the Hi. By doing so, it reestablishes equilibrium once the new concentrations are now equal to Kc in the equilibrium expression. So essentially, the reason why Le Chatelier's principle works, the reason why an equilibrium is going to shift if we add or remove some of the concentration of the reactants or the products, is that by doing that, we are making that equilibrium or those concentrations in the equilibrium expression no longer be equal to Kc. The shift in equilibrium to the right to lower the concentration of H2 and I2 and make the concentration of Hi higher is going to happen so that we reestablish an equilibrium where the ratio still works and Kc is still true. For a change in pressure, it works very similarly. If there's a different number of gas molecules in both sides of a chemical reaction, a change in pressure is also going to shift the equilibrium. However, Kc is still not going to change, just like we saw with the concentrations. So the pressure for the gases is also going to affect the concentration of those gases. So the explanation for why equilibrium shifts whenever there's a change in pressure is essentially the same as that for concentration. Because for gases, the change in concentration and change in pressure are related to each other. We can only change pressure by either reducing the volume or increasing the number of moles of a gas. Both of those are not just going to change the pressure of the gas, it's also going to change the concentration of it. And so the equilibrium is going to change, just like we saw with the concentration, to reestablish that Kc. Because when we change the pressure of a gas, we're also changing its concentration. And so the equilibrium needs to shift to reestablish the concentrations so that they're equal to the same Kc. Now, the only thing that can change the Kc, that can change the equilibrium constant, is temperature. The equilibrium constant is what is known as temperature dependent. We say that Kc is temperature dependent, meaning that when temperature changes, Kc also changes. As we saw earlier, so we go back a second, when we look at the equilibrium expression, there is nothing in the equilibrium expression that is related to temperature. Temperature does not change the concentrations of reactants and products. There is no T for temperature in this equation. So what is the only thing that's tied to temperature? Kc. Kc being temperature dependent means that Kc is going to change when we change the temperature. So Kc has a direct relationship with temperature whenever there is an endothermic reaction, meaning that when we raise the temperature for an endothermic reaction, Kc goes up. When we lower the temperature for an endothermic reaction, Kc goes down. And it is inversely related to the temperature in an exothermic reaction. So it's actually essentially the opposite, right? In an exothermic reaction, when we increase temperature, Kc decreases. In an exothermic reaction, when we decrease temperature, Kc increases. They have an inverse relationship. So depending on whether the reaction is endothermic or exothermic, Kc is going to have a direct relationship with temperature when an endothermic reaction, and an inverse relationship with temperature in an exothermic reaction. These relationships are essentially due to the same shifts that we studied in Le Chatelier's principle in section 2. They're going to cause those shifts in equilibrium. Why? If we have the equilibrium expression and we change the temperature, then if we change Kc, the concentrations of the reactants and products at equilibrium need to shift to match the new Kc. The equilibrium concentration in a reaction is going to shift so that the temperature changes adapt to the new equilibrium constant. So, for example, if we look at the reaction that we've been working along in the whole video, and we flip it, so we have 2HI is going to yield H2 and I2. This reaction, as it's written here, has a positive enthalpy change, right? Which means that because it has a positive enthalpy change, which is going to be endothermic, Kc and temperature are going to have a direct relationship. And we can see that in the data here. As we increase the temperature from 300 to 500 to 1000, the Kc for this reaction increases from 1.26 times 10 to the negative third to 6.25 times 10 to the negative third to 18.5 times 10 to the negative third. So the relationship between Kc and temperature is positive. It's a direct relationship. As temperature increases, so does Kc. Why? Because this reaction is endothermic. Because Kc changes, according to Le Chatelier's principle, the temperature is also going to affect the concentrations of all of these reactants and products at equilibrium, because they need to readjust to match this new Kc. So what this essentially tells us is a theory behind mathematics, actually, behind the Le Chatelier's principle and its relationship with temperature, pressure, and concentration. It's a mathematical explanation for why Le Chatelier's principle works, why this happens, why do the equilibrium concentrations of an equilibrium reaction change when we change either concentration, the pressure, or the temperature. Well, that's it for section 3. I will see you all in the next video to discuss how we can apply everything we just learned to gases in the reaction and to pressures instead of concentrations.